So if I want to find the value of y corresponding with the x value of -4/3, right? So we had already found the x values corresponding with the y value of 0, which was pretty easy. To find the y value corresponding with the x value of -4/3, again, I'm going to take my, whatever relation I have involving x and y, which would be the boundary function, and I'm going to replace each instance of an x, in this case there's only the one instance, with a -4/3. So the question is, how do you decide to multiply the Lagrange multiplier by t of xy instead of g? It actually doesn't matter, because if it's a constant, if it's a scalar multiple, then if I multiply it on one side versus multiplying it on the other, it's really just a matter of multiplying by a reciprocal. It's kind of like multiplying one side of an equation by 2 or the other side of the equation by 1/2. So as it turns out, it really doesn't even matter. Okay. So as long as you're basically just guaranteeing that they're a scalar multiple away from being one, from one being the other, then you're doing what you need to do. Right. So I could have put the Lagrange multiplier on the other side also. All right. So now I'm looking at, good question, -4/3 squared plus 4y squared minus 24 equals 0. I can just pop some of this in the calculator, just so, not in the thinking kind of mood right now, because I know -4/3 squared is going to be 16/9, but then I have to multiply. I'd have to get a common denominator, put that with the -24. I just not up for it at this point. Right. I think it would be 216/9, but it's not important. So yeah, so then I would subtract it, or add the 16, and I would get -200/9. So 4y squared minus 200/9 equals 0. All right, I can divide everything by 4, but if really I'm just going to end up solving for y anyway, I can just, before I do that, add the 200/9 to both sides, then multiply both sides by 1/4. Gets rid of the 4s here. So you get 50/9, which gives me a y equal to plus or minus 50, the square root of 50 over 3. The square root of 50 is really 5 radical 2, because essentially I'm just taking the square root of both sides. So I'm looking at 5 radical 2. I think I might have said 5 radical 3 previously, over a 3. So 5/3 radical 2. You could represent it any way you want, but I mean, that's as reasonable a way of writing it as any. All right. So I have the value of y corresponding with x. So I have some ordered pairs to work off of here. So I now know that I'm looking at some critical values of plus or minus radical 24. And, while I'm in a simplifying kind of mood, I mentioned before, or last class, that we didn't really have to simplify, but I already did it for the one. So now I feel obligated to do it for the other. All right, so this is going to be 2 radical 6. All right, so plus or minus 2 radical 6 comma 0, because x comes before y. And then plus or minus, -4/3 comma plus or minus 5/3 radical 2. All right, so these are our candidates. Ooh, left all the trimmings behind here. That's not good. All right, so these are all the candidates for extreme values. So these are my possible extrema. All right, so then it's going to beg the question of, okay, well, which one's the winner? Because it says find the extreme temperature, so we're looking for the highest and the lowest. All right, so I got 3 possible candidates here. 1, 2, 3, 4 possible candidates. Plus or minus 2 radical 6 comma 0 is really negative 2 radical 6 comma 0, positive 2 radical 6 comma 0. Then I have negative 4/3 comma negative 5/3 radical 2, negative 4/3 comma positive 5/3 radical 2. So all 4 of those are possibilities for the extreme values. Maybe we'll have more than one set of critical values that lead to extreme. So it's a question of, okay, well, how do we get there? I like the Desmos approach, and that is to say that we would substitute in, so sub into t of xy and find the highest and lowest values. So find the highest and lowest t. All right. So that's all Desmos work at this point. And it's not too crazy because it's really just getting an idea of which one's going to be the biggest, which one's going to be the smallest based on decimal values. And I'm just going to move this over here. It's starting to get a little crowded. All right. So all of the previous work led to this. So what I would do is I would take my t function, which is x squared plus 2x plus y squared. And I know I've gone over this before. I'll do it again, though. And when I'm substituting into a function using Desmos, I like to do it using A's and B's because I get sliders for my substitutable values. Okay? So instead of x, I use A. Instead of y, I use B. So I would write this as a squared plus 2a plus b squared. All right. And then it asks if I want a slider for each of them. It's a slider for all. I say, absolutely. You dang right I do. All right. So now I'm going to evaluate each possible pairing. Now, if you can get a slider to slide to negative 2 radical 6, congratulations. You're better at this than I am. I would imagine you're probably typing it in. So the B value is going to be 0 for the first ordered pair, the first set of ordered pairs. B value is going to be equal to 0. So my A value, I'm going to just type in a negative 2 rad 6. So that's the equivalent of that decimal. So we do kind of have to itemize it a little bit, but we can start getting into approximations here. All right, so we have negative 2 radical 6 comma 0 comma about 14.2. Then I'm going to do the same thing with positive 2 radical 6 comma 0. So there I just ditched the negative. That's fine. That's easy enough. All right, so 33.8 roughly. All right. So I know now that my maximum value isn't going to be happening at negative 2 rad 6 comma 0. It might be at the positive 2 rad 6 comma 0. We'll see. All right. So now I'm going to investigate these other guys. So negative 4/3 comma. And you might want to leave it as a radical 50/9 as a fraction. It might be just easier to type it in, but I've already made the adjustment. So 5/3 radical 2 comma something. We'll figure it out in a sec. So negative 4/3 and then negative 5/3 radical 2. All right, so those are decimal equivalents, and this corresponds to 4 2/3. I'll just write 4 Well, I'll write 4 2/3. I was going to write 4.7, but I had to change the order at the last second. Right, because it's entirely possible that that's the minimum value, and if it is, a little bit more accuracy wouldn't hurt anyone. Right. So I did the 2 negatives. Now I just need a negative and a positive. So I drop the negative here, and I get another. Okay, so this actually works out nicely. So I don't need this extra stuff. I could just write plus or minus here because it gives the same value, which actually ought to make sense when you think about it, because the function you're plugging into has only one instance of y, and that y value is squared. So whatever you plug in for y is going to be, irrespective of the sign. So it won't make a difference. Right? So it looks like the minimum temperature, that's not a min temperature, approximately, so I will go to decimal form here, 4.7. I said extreme temperatures. I got to imagine some measure in degrees. It just didn't get into, what scale. So I'm just going to say degrees. Max temperature. We're looking at about 33.8 degrees. I mean, if I had to take a stab at it, I'd probably be thinking Celsius. I wouldn't think Fahrenheit made too much sense. I'm thinking of extreme temperatures on a metal plate. 33.8 doesn't really sound very extreme in terms of temperature, unless you're talking about extreme on the low side, as in like really cold. But 4.7 is really, really cold if you're going in Fahrenheit. But in Celsius scale, that's pretty up there, that 33.8. So, zero is zero, so freezing. So it would be a little bit above freezing, and then close to boiling. Actually, it wouldn't even be close to boiling. Sorry, 100 degrees Celsius is boiling. It would be like what, in the 90, 100 degree Fahrenheit range, if I remember correctly, something in the low 30s. For whatever reason, it sticks out in my mind. I could do the conversion, just Google it, but my memory serves, it's in that neighborhood. Okay, but we can get our extreme values this way. It's dependent on their constraint function. So this brings an avenue to come up with extreme values that would have been a little bit too tricky, I would say, to do using something like the second derivative test. All right. So 58 is another problem that's kind of along the same lines, but you'll see that we jazz it up a little bit. All right, profit A company. What do we got in the chat here? Okay, no problem. The profit a company makes on producing X, Y, and Z 1,000 units of products is given by this model. And so just very vague. We don't really have a sense of what those products are, how big they are, or anything beyond. This is the profit function, and the manufacturing constraints force X squared plus 4y squared plus 2z squared to be less than or equal to 800, right? For whatever that means. Find the production parameters for maximum profit for the company. So we're looking for extreme value. Right? So you look at it and you say, all right, well, we got a primary function, that's a profit function. Right? So we're good to go there. If I want my first order partial, that's going to be really easy. Just the matter, I mean, it's linear, so it's really nice. I mean, we're talking about the equation of a plane, essentially. So, we're talking about linear components. So the derivative with respect to X is going to be 4. With respect to Y is going to be 8. With respect to Z is going to be 6. Okay, so that's not bad at all. Now the constraint model, we have, and And in this one, it's a little kind of on the nose, where like which one is the constraint function? Oh, the one that has the word constraint in it. So sometimes it's that obvious, right? So if I get everything over to the same side, because remember, I'm looking for the boundary. I'm not looking for the shaded area or shaded volume in this case within, right? So this is the equation of an ellipsoid. You can graph it in GeoGebra, but that less than or equal to symbol tells us that we're actually shading or taking into account all the volume that's captured within the ellipsoid. And just because we haven't gotten there yet, the third tech assignment deals with quadric functions. One of them is, so when we get there, you'll see, one of them is an ellipsoid, which is really just an ellipse that is in 3 dimensions. If you kind of imagine that. A good example of the visualization on that would be if you were to take those old problems from Calc 2, where you would take an ellipse equation and revolve it around an axis. That's along the lines of what you would get when you're talking about an ellipsoid, right? So in this case, I only care about the surface. I don't care about the substance, right? So kind of the opposite of not judging a book by its cover, right? All we want is the cover, right? We want surface and insubstantial. So x squared plus 4y squared plus 2z squared is going to be equal to 800, right? So that gives us the surface itself. Now, if I wanted to define this as a multivariable function, I would want to have everything over on the same side. And then I would want to define it as that multivariable function, which we would, we have x, y, and z in the equation. All right. It would be equal to, we use w or a lowercase omega, either way. But you can let it be equal to w, but we're going to say g, because typically for the constraint we use g. You can use whatever you want. It doesn't make a difference. But we're going to say that this is equal to g of x comma y comma z. All right. So now I could find my first order partials with respect to x, y, and z for the g function, which is 2x, 8y, and 4z. I mean, for something that's we're stepping it up in terms of the idea that it's going into 3 dimensions. I mean, it's not a three-dimensional function. It's a function of 3 dimensions. So it's actually a 4-dimensional function, with the 4th dimension being profit. All right. So we have all that going on, but we can also kind of appreciate the fact that even the more complicated cases sometimes work out sort of not so complicatedly. And this is not terrible, right? So we can use our Lagrange multiplier. I could say 4 lambda equals 2x, or I could say 4 equals 2 lambda x. It doesn't matter where you put it, because again, lambda is a constant multiple, a scalar multiple. All right, so this time I'll put it on the right-hand side as opposed to the left-hand side. That's why I was telling you that that first page of the notes on Lagrange, it's very much, very textbooky, and it doesn't really give you the true essence of the Lagrange multiplier concept. This hopefully is a little bit better. Seeing it in action. All right, so I could do a few different things here, and one of them, I think, is the obvious thing, is to simplify. All right, so the issue is maybe the first order partials were a little too simple, because at first glance it's like, oh, this is great. It's really nice and easy. It's not going to be a problem at all. It's going to be super easy, barely an inconvenience. The issue that we run into is that it isn't like the nice cases that we had on the previous page where the x's would cancel or the y's would cancel. It's not quite like that, but it won't be that bad. So let's take a look at that. I wanted that to autocorrect. There we go. The first one, just something very simple. Actually, all three of them, we'll do them all in the same breath here. They're all even numbers divisible by 2. The first case I can actually only divide it by 2, but the second case I can divide it by 8. So I can really just kind of clean this up somewhat. So we're looking at 2 if I turn my pen on, 2 equals x lambda. I'm looking at 1 equals y lambda. And if I divide the last one by 2, I'd be looking at 3 equals, this one I'm kind of stuck with something as the coefficient on the right, 3 equals 2z lambda. All right. Now, you kind of boxed in because I can solve for lambda in terms of x, in terms of y, in terms of z, then start setting them equal to one another. But I can also go the other way, solve for x in terms of lambda. All right. So I could say that x is equal to 2 over lambda, y is equal to 1 over lambda, and z is equal to 3 over 2 lambda. All right. Now it's at this point where you might say, oh, dang it, I wish I put the lambda on the other side, because then I would have something that had lambda, I wouldn't have lambdas in the bottom of fractions. Right. In the end, it's not going to make much of a difference. So I wouldn't worry about that. Right. Because again, and this is very important to realize, lambda is not a variable. It's just an unknown scalar. Right. So whether you go through the process and solve, you might end up with a 2 or 12 or something like that. But worst case scenario is you get something like 1 over lambda equals 1/2, in which case you're like, oh, okay, well, that just means lambda. Right, so that part should be easy. The boundary function relates x, y, and z to one another. I now have a way to swap out each one of those variables. Instead of having one equation with 3 variables, I can have one equation with 1 variable, with that variable being the scalar lambda. Lambda. Right? So I'm going to swap out x, y, and z for these 3 values. All right, so 2, that's not a 2, not even close to a 2. 2 over lambda squared plus 4 times 1 over lambda squared plus 2 times 3 over 2 lambda squared minus 800 equals 0. My moment of hesitation there was, should I just add the 800 to the other side? I mean, I'm going to want to isolate lambda, but then I caught myself and like just kind of told myself, hey, like let's hold off on that for a second, because if this ends up being quadratic, I'm going to want everything over to the same side and go from there. So, just play it by ear here. So 4 over lambda squared plus, as it turns out, 4 over lambda squared plus, so this is going to be 2 times 9 over 4 lambda squared minus 800 equals 0. All right. I can combine some like terms, but I could also get a common denominator. Before I get a common denominator, let's wipe out this 2 here with the 4 twice. So if I want to get a common denominator, I could, but let's also combine these, take advantage of that. So it's 8 over lambda squared plus 9 over 2 lambda squared minus 800 equals 0. Once you realize that you're going to be able to combine all the variable parts into one term, then you decide, okay, maybe I should bring the 800 to the other side, right? I am going to multiply both the top and bottom, I should say, by 2 here. So I'll have a common denominator. I'm looking at 16 plus, so these two together. Oh, I love it. 16 plus 9 is going to be 25. So we're looking at 25 over 2 lambda squared. And then I'll swing that 800 to the other side. And I should, preface is not the right word, but I should make the statement that none of this algebra is necessary for me. I don't need you to show me the algebra. This is just for the algebra lovers out there, right? For all the algebra lovers out there. You know, it's really just to go through it and show you, because you could just do this on Desmos, and I'll take you through that in a second anyway. All right, so 1600 lambda squared, just doing a little cross multiplication. 1600 lambda squared equals 25. So lambda squared is going to be equal to 25 over 1600. Lambda would then be, if I'm taking the root of both sides, 5 over, it's going to be 40. So it's really going to be 1/8, right? So plus or minus, I'll write it as 5 over 40, but it's really going to be plus or minus 1/8. All right, now it's not our final answer, but it's a step in the right direction, right? It's actually a large leap in the right direction. Let me be clear about that. Like, we're almost done. Because I have a habit of doing that, where I say, oh, well, it's not our final answer. We still got like half an hour's worth of work to do. It's more like, it's not our final answer. We still got like 30 seconds more of work to do, right? But before we do that 30 seconds more of work, let me show you the alternate approach, which would have taken this work and just pop it right into Desmos, and that would have been it, right? So it's just, if you want to figure out how to type in a lambda into Desmos, by all means, go for it. I'm just going to use x instead, right? So 2 over x squared plus 4 parentheses 1 over x. And you know, my crappy lambdas look almost like x's anyway, so if you kind of blur your vision, you can convince yourself that they're x's. It makes you sleep at night. So you type in the equation, but without the equal 0, right? Well, what we really want is the function. So I could type it in as y equals. I could type it in as f of x equals. I'll type it in as y equals. I don't like it. The fact that Desmos allows this is convenient, but it's also kind of incorrect, where you just type in the expression and it graphs it like it's a function. It kind of rankles a little bit, but you know, it's easy to get over once you realize that half the time you forget to type in the y equals anyway. Right, but then all you're looking for is when this equation is equal to 0. So tap on the zeros of the function, and it'll just tell you what they are. Right, 0.125. If you don't recognize that as a clean fraction 1/8, then what you can do is type in the 0.125. It'll present you with the fraction converter icon right below the 2. Just tap on that, and it'll just spit it out for you. All right. So you could do it that way. I mean, there's other ways to do stuff like this, but I think that's probably the most, I guess, manageable, probably, right? So, I mean, it does involve a lot more typing, and some people look at it as a trade-off. I'd rather do the algebra. I don't know that I would rather do the algebra, but I would rather, in some cases, do the algebra, and in other cases, do the Desmos, depending on what my preference is in that moment. Right. So I learn them both and hope that I don't have to be presented with an impossible task, something that, I can't use either of them for, which won't happen in my class, I'll tell you that. But we have the lambda values. Some are, one is positive, one is negative. Contextually, we have reason to think that maybe we don't want the negative, but sometimes negatives are okay. So we got to keep that in mind, right? We do have a relationship between X, Y, Z, and lambda, right? If ultimately what we're looking for, again, the profit a company makes on producing X, Y, and Z thousand units of products is given by this, find the production parameters. That sounds like X, Y, and Z, all right? So that's what they're asking us for. So X, Y, and Z is the number of units. So now I have license to dismiss the negative lambda, because when I plug in a positive lambda, right? So I'm gonna make a little note here. I'm not going to use function notation. I'm just going to say if lambda is equal to 1/8, I get 16, I get 8, and then I get 12. I'm doing keep, change, flip, 8 times 324 divided by 2. All right, so 1,000. All right, so units specifically, and that's reasonable, I think, for a problem in which we have no idea, we have no context. Like we're assuming, okay, it's a production, a company that's producing widgets or whatever it is, objects. We don't know what they are, so we don't know what's a lot, what's a little, but we can damn well be sure that the negative value isn't going to make any sense in this context. Because if I plug in a negative 1/8, it's just going to give me negative 16,000, negative 8,000, negative 12,000. Right? Now, there is a time and place for a negative value, even in this kind of context, where if I wanted to know how many items I would have at the end of the month, for example, based on particular constraints, then I could be looking at something like, a negative value being meaningful. Because what that could tell me is how many items I'd be short at the end of the month. Like if I got negative 8,000, that would mean that I would be short 8,000 items at the end of the month. All right, that doesn't seem to be in play here, but you never know. It's always possible. All right. Yeah. Anyway, so the next problem that we're going to talk about, I had a fleeting thought and I just kind of lost it there for a second. That's kind of the way my brain works sometimes. The next problem is involving multiple constraints. So it's a pretty fun problem. Also a Lagrange multiplier question. But now you experience the full power of God. Right, so to optimize with two constraints, it's a linear combination between your partials for your parameters. Now, you see the notation here, the upside down triangle. That's unfortunate because I moved some things around and we talked about gradient and directional derivative after we talked about Lagrange multipliers, although in most textbooks it comes before. I don't like that sequence, so I took the liberty of changing it myself. So every now and then notation like this will kind of creep in. but it is correct. And unfortunately, it's not even a typo. But what this represents, when you see an upside down triangle, you're talking about the gradient or the a set of directional derivatives associated with a particular multivariable function, right? So I'll get into that a little bit more later, but what this is really telling us specifically is that we're going to have two Lagrange multipliers, right? Instead of just lambda, we're also going to have another multiplier that we're going to call mu. Now, you can call it whatever you want. It's just the standard notation involves the two Greek letters, specifically lambda and mu, right? And you just incorporate another Greek letter if you had a third constraint, right? But you'll see here that now it really does matter what side of the equation has the Lagrange multipliers, because now it's a sum of the two constraint derivatives, right? So we don't have the wiggle room to go either way. We have to be specifically on the right-hand side with our Lagrange multipliers, right? So you see this problem here. And, I go a little crazy with the diagrams because I want to at least give you some sort of ideal, or at least in my opinion, ideal perspective related to the whatever the circumstance, whatever the scenario is, rather than just giving you the context or absence of context and just saying, oh, just kind of imagine it, So all these diagrams here were in the hope that you'd be able to kind of piece it all together between the ellipse function, the original multivariable function, and how they intersect with one another and how one projects upon the other. Just kind of looking at it from different perspectives. Same idea here. We're looking at a plane, x plus y plus z equals 12, and a paraboloid, right? They intersect in the form of an ellipse, right? What we want is the point on an ellipse is closest to the origin, right? So I think it's pretty easy to see. I don't think it's unfair to say that this is showing a plane slicing through. If you know that cone-ish shaped figure is a paraboloid, then it's pretty clear to see that this is a plane slicing through the paraboloid. And then I think it's also pretty easy to see that a circular path is created by that intersection, right? Maybe you wouldn't recognize that it's an elliptical pattern, but it is. But if you think back to pre-calculus and discussions of conic sections, you might remember the case where they took, I don't know, your teacher should have done this. They took a cone and they showed you the different ways in which you can slice through the cone. You could slice through it horizontally. You could slice through it on an angle such that you don't go through the base, and then an angle such that you do go through the base, right? And then if you had two opposing cones, tip to tip, and went straight down, or even at an angle, but so that you went through both bases, you would get all the different types of conic sections that you could possibly get by the cross section of the cone. Cone cross sections, conic sections, right? So this is really just kind of that same idea, just except we're working with a paraboloid rather than a cone, right? So that's what the first two diagrams are trying to display. Now the third one, that's the weird one. What I did was I took the ellipse, and so I took the paraboloid and the plane and the intersection that's created, that ellipse that was created by that intersection. I stripped everything else away and I just grabbed the ellipse, left that floating in space. So it's really just this piece here. That's what this is, right? So then you might look at it and say, well, where the hell does the sphere come from? Well, the sphere, that's the distance from the origin, because tucked away in the middle of this, in here somewhere, is the origin. And the distance outward from that origin would create, if it's a fixed distance, it would create a sphere. Now you might look at this and say, well, it doesn't look like a sphere. It looks flattened. It looks more elliptical. I did the best I could. Right? So it just ended up looking that way. Right? So it's supposed to be more elliptical than I'm sorry, spherical than elliptical. It's just the best I can do. Right? So any point on the surface of this sphere, so any point, now it's in perspective. So, it's like the near side surface, the far side surface, it's kind of tucked away inside, all the way out over here. All these distances are supposed to be the same. Even this distance right to the tip of that ellipse, those should all be equivalent to one another. All right. So we have information, and that's good. The original function, or the primary function, the thing that we're working with, the thing that we're trying to optimize. But you think back to Calc 1, there was always two functions that you worked with optimization: your primary function and your secondary, or your support function. The primary was the one that you were using to optimize, and the secondary function was the one that you would use to maybe swap out a variable in your primary function. The same idea here, except we're not going to swap out variables. All right, but you start thinking, okay, well, what am I trying to optimize? I'm trying to optimize the distance. Right, now we talked about distance. Distance in 3 dimensions is the change between a point in space and some fixed point for X, Y, and also for Z. One day I'll develop a good habit of doing my radicand, writing out my radicand before I actually write the radical symbol. I tried doing it. I always forget. It's bad news. So now I got to undo this. Although I can't complain too much, when I first started teaching, it was still chalkboards. And I was one of those teachers that, I was a rookie, when I first started, came in with full-blown suit, first day on the new job. My father was like, you gotta dress up. It's the first day, like you're at work. Yeah, at the end of the day, I was covered in chalk dust, and a bunch of veteran teachers laughing at me. They're like, that's the last day you're wearing a suit, right? I'm like, yeah. Yeah, no problem. I know exactly what you're talking about. So we have d squared. If you remember from, I believe it was last class, d squared is equal to this whole shabiggity bangity boom. Right. So all that whole thing about the chalk, that's just me saying that I should probably stop complaining about how challenging it is to write on my iPad with my Apple Pencil while using Zoom and screen sharing functions and recording to YouTube and all that stuff, because it is a far cry from where I started. Okay. So this is a function I could work with. You remember we defined it previously as f of x comma y because we were able to swap out a z. I don't know that that's going to happen here, but I do want to somehow make this into a function. Right. So we're going to sit tight on this until we take a look at all the other things that are going on. Right. So I'm going to reduce the size a little bit. And now I'm going to bring the plane the paraboloid, or the plane and the parabola into the situation here. All right. And see what we're up against. Because I'm going to be stuck in my distance formula. I'm going to be stuck with the x and the y. I'm sorry, the x, y, and possibly the z. but I do want to be able to swap out the x sub o, y sub o, and z sub o's. Now, reading the question again, it's find the point on the ellipse closest to the origin. Find the point on the ellipse that's close to the origin. Now, this thing is really constrained in two ways. One, it's got to be the intersection between the paraboloid and the ellipse, right? So there's that idea that we have those two models, those act as our two constraint functions. Now we can handle that one of two ways. We could find the intersection between those two functions and go from there, or we could work with them as our two constraint functions and apply the Lagrange method for two constraints, which is what we're going to do because it's part of the lesson. The other constraint, I'm going to air quotes constraint there, is the fact that we're looking for a distance closest to the origin. Origin is 0, 0, 0. So that gives us a fixed point that's known. All right, so it's the distance between some point in space, some unknown point in space, and some very well-known point at the origin, right? A fixed point at the origin. So I can say d squared is really equal to x squared plus y squared plus z squared, right? Which would be a lot more complicated if it wasn't the origin. You know, if it's the distance between two functions, two moving points, you know, like x, y, and z, that's variable, as it will be here, and also some other x, y, and z that's related to other constraints. Right? Very complicated stuff, not something that you need to bother about when it comes to a test in this class. But it is an extension of this idea. All right. So these two constraints, like I said, I can look at them independently, or I can look at them together. Right? If I look at them independently, I would be bringing everything over to the same side. So x plus y plus z minus 12. I wrote the whole dang thing again, which would make the constraint function, I'll call it g of x, y, z equal to x plus y plus z minus 12. Right? Now the other one, we kind of look at it at first glance, it's like it's already equal to z. So can we call it f of x comma y? Well, we could, but the thing is, everything else is in terms of x, y, and z. Right? So, like for example, I'm going to call this one f of x comma y comma z. I already call this one g of x comma y comma z. So this last equation, yeah, I'd love to call it, well, it would have to be h, but I'd love to call it h of x comma y. But everything else is in 4 dimensions, functions of 3 variables. This one also has to be a function of 3 variables. So I'm going to rewrite this by subtracting z from both sides. X squared plus y squared minus z is equal to 0, and make this h of x, y, z is equal to the same thing, x squared plus y squared minus z. All right. And again, all of this, taken with a grain of salt, because if you wanted to, you could find the intersection between these two functions, which would be an ellipse equation, and then just use that ellipse equation as a single constraint. All right. But we're trying to learn skills, so I'm trying to do something here, man. So it's kind of necessary to do it this way. All right. At least for this problem. So f sub x, 2x, f sub y, 2y, f sub z, 2z. Not too bad. For my g's, all straight up ones, right? Sign up for that any day. And then my h is two x, 2y minus 1. All right. So the model is saying, again, it's a linear combination between the first order partials for your constraint functions and the first order partial of your function to be optimized. So long story short, we're relating these three components, these three, and these three. So we'd be looking at 2x is equal to 1 lambda plus 2x mu. We're looking at 2y equals 1 lambda plus 2y mu. And 2z is equal to 1 lambda minus just a clean mu. There's no y there, so that's good news. Let me get my highlighter going here. Now the rest of the problem is algebra. It's like, thank you, Captain Obvious. And what I mean by that is that what I said was an obvious statement. No, what I mean is that it's the approach that you're going to use is going to vary from problem to problem based on what makes sense algebraically. The last two problems that we did, we used two vastly different approaches, but they still ultimately had the objective in mind of finding the values of x, y, z, and in this case, lambda and mu. Right? So whatever it takes to get that job done is what we got to do. Here, it looks like we could be going down a road of systems of equation techniques. You know, we have two constraint functions, but one actually out of those two constraint functions, they both relate x, y, and z to each other. So we can start there. So we have x plus y plus z is equal to 12, and we have x squared plus y squared minus z is equal to 0. Right? So what we could do is streamline this at least a little bit so that instead of having two equations with 3 variables, we would have two equations with 2 variables. Right? And in order to do that, we would probably, at least I would think, want to try to solve one or both of the, or all 3 of these equations for x, y, z respectively. The thing that makes it tricky is that the one that's easiest to work with, z, is the only one that's easy to work with. Right? The other ones you got to do a little bit of extra housekeeping along the way. Right? So let's actually take a look at these before we start diving in, making substitutions. Let's see what shakes out. Right? So in each case, I can solve for lambda. 2x minus 2x mu, 2y minus 2y mu, so then once you do that, you take a quick look and see, okay, well, what did that do for me? Is there any benefit of going further, et cetera, et cetera? Well, I do see that we have a common factor. I could pull out a 2x here. Leaves me a 1 minus mu. I could pull out a 2y here. Also a 1 minus mu. All right, we got a commonality here, so we might be on to something. All right. The other one, I don't have a commonality, so I'm just going to leave that other one the way it is. since both of these are equal to lambda, I'm going to get a fresh new color in here. Both of these are equal to lambda. They are therefore equal to each other. So I could say, therefore, 2x times 1 minus mu would be equal to 2y times 1 minus mu. And the only thing that differs from left to right is the x and the y, so we can conclude that x and y have to be the same. All right, that doesn't help us with this one here, the lambda equals 2z plus mu, but it does help us with our constraint functions. It took something that was probably, I don't want to say it was impossible previously, but it was going to involve a lot more work. And it made it, all right, just one step closer to same, I suppose. So now what I can do is I can replace one of the two variables, either x or y, with the other. So I'm gonna keep x and get rid of y. So it'll be x plus z equals 12, and x squared plus x squared minus z equals 0. All right, and that's just to show you the substitution, because I know that you're all capable of making the additions of, or finding the addition of two like terms. You know, I didn't want to insult you, but so we're looking at 2x plus z equals 12. 2x squared minus z is equal to 0. All right. Now, you look at it and say, okay, well, I think maybe we could substitute a z in now, but then you look at it, if you look at it really carefully, you realize that I have two equations with two variables. So it's a system that can be solved. And that system can be solved through addition or elimination. You know, we don't have to do anything too fancy like reduce row echelon, because, and actually we couldn't, because one of them's got a power of 2, the other doesn't. But what we can do is just add the two equations together. And in this case, we would get 2x squared plus 2x equals 12. Bring over everything over to the same side, you know, solve. It doesn't matter what method you use. This time I'm just gonna cut right to the chase and go straight for the Desmos calculator. So I'm going to write y equals, this is another way of doing it, y equals the left-hand side, y equals the right-hand side. See where they cross, right? Because that's what a function-related equation is. It's the intersection of two other functions, right? We're just looking for the x values, so we get x equals -3, +2. So now I know x, which means I know y. I have the corresponding values for y, because I know x and y are the same. So I'm good there. So this is actually kind of starting to take off on me, just by making a simple recognition along the way that there was a common factor. Right, so it's a very similar yet different kind of feel to it, because it's algebra, but we're doing different algebra than we did before, right? So our values for x, right? So these are possible extrema. -3, -3. And I could even put the assumed comma in there. Now this is going to be a 4-variable situation here. So it's really just a question of how far do you want to go in your notation. So 3, 3, knowing that, I'm sorry, -3, -3, knowing that x plus y plus z is going to be equal to 12. Right? If you want, you can just kind of reorganize that somewhere off on the side. You can do that like right here. because z is equal to 12 minus x minus y. So it's really 12 plus 3 plus 3. So 12 plus 6 is going to be 18. So that's one possible extreme. The other is 3, 3, and then 6. Right? These are their possible extrema based off of this relation here. So we knew these two values. Oh, sorry. Why did I do that? No one knows. It was a 2. I just wanted it to be a 3. All right. So 12 minus 4 is going to be 8. All right. So based off of this relation and this information, along with this information, we get these two values. All right. So not our final answer, but we're close because, I mean, it's possible that one of them gives us the longest possible distance from the center, from the origin. You look at the ellipse, it's kind of like the Earth's revolution around the sun. You got the shortest day of the year and you got the longest day of the year, based on its positioning with relation to the sun. All right. So not quite apples to apples, but it's still the same idea. We do have another possible extreme value, which would be related to this distance. All right. We definitely don't want that one. That's the furthest a point on that path could be away from the origin. I don't want that one. I want the closer one. So what I would then do is go into my distance formula and figure out which one gives me the smallest distance. So d, as we know from before, is equal to x squared plus y squared plus z squared. Right, and so we just pop in this information. So d is going to be for evaluating it properly. So it's really just for the sake of not writing d of -3, -3, 18. So I'll write at -3, -3, 18. D would be equal to the square root of, we're looking at 81 plus the 162, so 270, something like that. And so 9. Oh, actually, that's not even close. 9 plus 9, because I squared 9 again for some reason. Square root of 342. Yeah. Sounds pretty big. All right, so three, 4, 2, 4, 2. All right, so it's about 18.5. And so if we do it at 228, D is going to be like a 64 plus a couple of 4s is going to be root 72. Again, I'm just going to double check. I'm doing math so good today. Yeah, 72. Right. So then root 72, about roughly 8.5. All right, so this would be the shortest distance. All right, but you could see here it's a pretty beefy process. A lot of stuff going on, and in fact, the easiest part I'd say was actually finding the derivative. It's like the calculus was nothing. The understanding of the setup, that was pretty tricky, and then from there the algebra. It's always the algebra, though. You know that. Oh yeah, good call. It is asking for the point that's closest. The shortest distance would be 8.5, but the point that's closest is going to be the 228. Very good. Thank you. Thank you. Good. The cheese. All right, so stop that recording, and we're